Welcome back. Let us continue our study of Chapter 4 and move to Section 4.4 about reflexive spaces. We already defined the notion of a reflexive space, but let us recall it because it's very important. If you have a norm space E and J is the canonical injection between E and its bidual, so J is defined by Jx of f is equal to just f of x. If J is surjective, we say that E is reflexive. Okay, so otherwise stated, E is reflexive if J of E equal to E double star. Now, to test your understanding, so of course in this case we identify E double star with E. Prove as an exercise that the following conditions are equivalent. J is reflexive, meaning that J of E equal E double star. Second condition, J of the unit ball, of the closed unit ball, is the corresponding closed unit ball. So J maps the ball into the ball, onto the ball. And third condition, J maps the unit sphere into the corresponding unit sphere. Fourth condition, the unit sphere of the bidual is contained in J of BE. And fifth condition, the unit sphere of the bidual is contained in J of E. So all these conditions are equivalent. So please take a paper and a pen and prove these simple relations, equivalence. You may want to do a circular proof. 1 implies 2, implies 3, implies 4, implies 5, implies 1. It's very important to understand that. And also as an exercise, prove that a reflexive space is necessarily a Banach space. Okay? Try to think why this is true. Okay, now in order to prove the main result of this section, we need two lemmas. Okay. First lemma is known as Goldstein lemma. If E is a norm space, then the image of the unit ball of E is dense in the unit ball of the bidual for the weak star topology of the bidual, because now we have also three interesting topologies on the bidual. We have the operator norm topology, we have the weak topology, sigma of E double star E triple star, and we have the weak star topology, which is sigma of E double star E star. Okay, so we have density here and the smaller one, which is the weak star topology. Okay, to prove that, we reason by contradiction. Okay, so how do we prove that a set is dense? A set is dense if, so we have to prove that the closure of J of BE is equal to BE double star, the closure in the weak star topology. Okay, so it's enough to prove that any element in E double star is in the closure. So suppose that this is not the case. So we have an element psi0 in the unit ball of E double star, and that it's not in the closure. What does it mean? It means that there exists a neighborhood in the weak star topology of psi0 which does not meet the set J of B. Okay? This is a characterization of closure of a set that we discussed in chapter 0. Now, of course, from the definition of the weak star topology, this neighborhood contains a basic neighborhood of this form. Okay, so here just instead of xi, you take fi because this is the weak star topology on the dual. So this basic neighborhood is of the form the set of all xi in the bidual, such that xi minus xi0 evaluated at fi at finitely many I, okay, is between minus epsilon and plus epsilon. Okay, so this neighborhood does not meet J of BE. What does this mean? It means that if x is in BE, so Jx in J of BE, then Jx is never in W. Okay, no matter for every x in BE, Jx is not in W. Okay, what does it mean? It means that it's not in this neighborhood. So we have to negate this. It means that for every x in BE, there exists an index I from 1 to k, such that Jx minus xi0 at fi is not less than epsilon. So it's bigger or equal than epsilon. Just replace xi by Jx. Okay, and by definition, Jx of Fi, you can write this as Jx of Fi minus Xi0 of Fi. But by definition, Jx of Fi is just Fi of x. So we have this condition for every x and b in the closed unit ball of E. There exists an index between 1 and k such that Fi of x minus Xi0 of Fi in absolute value is bigger or equal than epsilon. Okay, and now construct this map phi of x from BE star, from BE into Rk, whose components are just F1 through Fk. Because once again, recall that Fi of x is a real number. Okay, and consider in Rk the vector of components Xi0 of F1, Xi0 of F2 until Xi0 of Fk. So we get a map from E or from BE, if you like, to Rk. Okay. Now, this condition states that the distance, so if one component actually, so equip here Rk with any norm you like. You can take the Euclidean norm if you like. So if the distance between one component of phi of x to the corresponding component of C is bigger or equal than epsilon. So this means that the distance between phi of x and C is at least epsilon. And this means that when you take the nth, this means that the distance from the point C to the image of B is bigger or equal than epsilon. Okay. So in particular, C does not belong to the closure of phi of B, because the distance vanishes if and only if C is in the closure of the set, as you know from metric topology. Okay, so now what do I have? I have a convex compact set singleton C and a convex set phi of B. Why is it convex? Because B is convex and phi is linear, and the image on the linear map of the convex set is convex. So we can separate C and the closure of this set actually, because it's closed now, strictly by a hyperplane. So by a closed hyperplane. Of course, it's closed because we are in Rk. So this is just Hanbanach in Rk, not in E. So all hyperplanes are automatically closed. But what is a linear map from Rk to R? As we know from a previous discussion, a linear map is just a generalization of the equation of a line or a plane. So this linear map is actually a combination of, so I can write my map as sigma of alpha of beta I times xi, if you like. So this means that, and the delta here plays the role of epsilon in the definition, okay, because I already took epsilon. So okay, so this is just actually the value of the map evaluated at phi of BE, and this is the value of the map evaluated at the point C, right? If you call this map H, if you like. Okay. So the separation tells me that we have these inequalities. Okay. And now I can rewrite this term because everything is linear. This is the sum of BI-FI evaluated at x. So I can write as sum of BI-FI evaluated at x. So just the same thing, another notation. And here actually also I can write it as Xi0 evaluated at this, because now Xi0 is an element in the bidual. So it acts on elements of F. So this is just a notation. This is equal to this, and this is equal to this. Okay, but now this is true for any x in the closed unit ball BE. So, and this is an element in the dual. So when I take the supremum over x in the BE, I get the norm of this guy. And now the value by the fundamental operator norm inequality, the absolute value of this guy, or just this guy, is less or equal than the norm of Xi0 times the norm of this guy. This is the basic definition. So the first inequality tells me that the norm of this element in the dual is less or equal than alpha minus delta, because this is just the supremum. And the other inequality tells me that, so this is less than norm of Xi0 times the norm of this guy. But norm of Xi0 is less or equal than 1 because I took psi 0 in the unit ball of BE double star. So the second one tells me that alpha plus delta is less than the norm of this guy. And this is clearly a contradiction, because the same number should be less than alpha minus delta and should be bigger than alpha plus delta. So it's a contradiction. And therefore, my assumption was not true. So therefore, J of BE is dense in BE double star with respect to the weak star topology. Okay, and as a corollary, it's a good exercise to test your understanding. Prove that J of E is dense, the whole space, the image of the whole space is dense in the bidual for the weak star topology, of course. Okay. So the second result before we prove our main theorem is the following one. So once again, we have the canonical injection J between E and E double star. Then when I equip E with the weak topology, and when I equip E double star with the weak star topology, then J is continuous. Of course, J is continuous when I equip E with the norm topology and E double star with the norm topology. But here I'm considering other topologies weaker than norm. Okay. And this is the first thing. And second thing, if E is reflexive, then of course, since J is surjective and injective, it has an inverse. The inverse of J is also continuous between these topologies, and therefore J is a homeomorphism if E is reflexive. Okay, so let us prove continuity of J. Here I go back to the discussion of section 4.1 about the smallest topology making continuous. So if you recall proposition 4.2, how do I know that? So this is this in the terminology of section 4.2. This was the space Z. Okay, how do I know that a map from Z to E double star with the weak star topology is continuous? I consider this diagram. It's very important always to go back to this diagram. Okay, so J is continuous if and only if psi f of J is continuous for every f in the dual of E star. Okay, what is psi f? I should have called phi f in the notation, but here, in order not to make confusion between phi sub f, this is so psi sub f is just the map that to each psi associates its value at. So it's the evaluation map, if you like. Okay, so why? Because the weak star topology is by definition the smallest topology making all these maps continuous. Okay, so we are going to apply proposition 5.2. Okay, so why this composition is continuous? This is easy, because psi f of J evaluated at x is just by definition psi f evaluated at jx. So this is just jx of f, so which is by definition of J f of x. Okay, but when I equip E with the weak topology, this map is continuous. Okay, therefore the composition is continuous. Okay, so actually psi f of J is just f, and when I equip E with the weak topology, f is continuous. So psi of f of J is continuous. So this could be hard to, but take your time and think of it. Okay, so this is just an application of proposition 4.2. Therefore, I proved that for every f in E star, this composition is continuous, and therefore by proposition 4.2, J is continuous. So this proves the first part of the claim. Now, of course, there's another proof that uses proposition 4.11. We know that J is continuous strong. Okay. According to proposition 4.11, it's continuous weak. So just put weak here. And this implies continuity weak star. Why? Because if it's continuous weak, what does it mean? It means that the inverse image of a weakly open set in E double star is weakly open in E. And therefore, the inverse image of a weakly star open is weakly open in E, because weak star is contained in weak. Okay, so this is another way to prove that. So we have two ways to look at the same thing. Okay. Now the converse. If J is surjective, so J minus 1 exists, and now I need to prove that J minus 1 is continuous. So again, I use proposition 4.2, but the set equipped with the smallest topology is here E weak. So to prove that J minus 1 is continuous, I need to prove that phi f of J minus 1 is continuous, where phi f is just f. Okay? Because the weak topology is the smallest topology, making all f in E star continuous. And again, this is trivial, because f or phi f of J minus 1 of xi is f evaluated at J minus 1 of xi. But by definition, this is J of J minus 1 of xi, the definition of a J. This J of J minus 1 of xi evaluated at f. And this is just xi of f. And the map that to each xi associates its value at f is continuous when E double star is equipped with the weak star topology, because this is the definition of the weak star topology. The weak star topology is the smallest topology making continuous all these maps. So these maps are continuous. And that's it. So this proves that J is a homeomorphism. And actually, if you look at the proof of the second part, we don't need to assume that E is reflexive. If E is not reflexive, we can prove that J minus 1 from J of E equipped to the weak star topology to E with the weak topology is continuous. Just same thing, actually. Okay, just same proof. Okay, because the weak star topology of JE coincides with the substrate topology inherited from E double star. This is also easy to check. Okay, so having proved these two preliminary results, we can prove the main result of this section, which is known as Kakutani theorem. So in a norm space, if E is a norm space, then E is reflexive if and only if the closed unit ball is weakly compact. So I have to prove two implications. Suppose first that the closed unit ball BE is compact in the weak topology. Okay, now by the previous lemma, J is continuous in the indicated topology. So when I equip E with the weak topology and E double star with the weak topology, therefore the image, know that the image of a compact set under a continuous map is compact. Therefore, J of BE is compact in E double star equipped to the weak star topology. But Goldstein lemma tells me so that, okay, so if it's compact, then it's closed because the weak star topology is Hausdorff. Therefore, I know that J of BE is closed. But Goldstein tells me that it's dense. A set, what can we say about a set which is both closed and dense? It means that it's equal to the whole space. So J of BE is equal to the whole space. And that's it, according to the exercise that we started with. So we proved that J of BE is equal to BE double star. And this is equivalent to saying that E is reflexive, or J is surjective, same thing. Okay, now conversely, suppose that E is reflexive. Then we know from the starting exercise that J of BE is so J maps the ball into the ball. And I know that BE double star as a ball in a dual space is compact when the space is equipped with the weak star topology. Okay? But J minus 1 is continuous in the indicated topology. Therefore, the image of BE double star under J minus 1, which is just BE, is weakly compact, and therefore the closed unit ball is compact in the weak topology. That's it. Now, to test your understanding, I want you to prove this corollary, two corollaries actually. First corollary, a norm space E is reflexive if and only if every convex strongly closed and bounded subset of E is weakly compact. Second corollary, in a reflexive space, a set is weakly compact if and only if it's weakly closed and bounded. Okay, so this gives the familiar characterization of compact sets that you are familiar with from Rn. So in Rn, a set is compact if and only if it's closed and bounded. So here we have something similar. Okay, but this is not true if the space is not reflexive. Okay, so I think I will stop now in order not to make a very lengthy video, and I will continue the second part of this section next time. So thank you for your attention and see you soon.